Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem ID 1415, the kth lexicographical string of all happy strings of length n. This is a very good backtracking question recently asked in Google and Microsoft. Let's have a look on the problem statement. They are saying a happy string is something that consists of these two values. Happy string is going to have these three characters and si is not equal to si plus 1. Every character is not same as the next character for all the string. So this is just a definition of happy string, given some examples. Apart from that, we are also given two integers n and k, and also consider a list of all happy strings of length n sorted in lexicographical order. Okay, they are asking us to do this and then return the kth string of the list of this list, otherwise return an empty string. Okay, let me explain this problem statement to you with the help of an example. First of all, they are saying that what is a happy string? Happy string is a string that following these two criteria. First criteria is the string is going to have characters A, B and C, and apart from that, every character, every ith character is not same as I plus 1th character. So this condition should be true for all I equal to 0 to n minus 1, n minus 1 excluding. Okay, this is our happy string. If I take a couple of examples, let's say these 6 examples I have taken ABC, whether it is a happy string or not. This is a happy string because none of the character is same as the previous character. This is also a happy string. This AC is also a happy string. What about ABBC? This B character at index 2 is same as the B character at index 1. Index 1 character is not equal to index 2. This should be there, but here it is equal. So this is not a happy string. What about this ABCAC? This is also a happy string, but this is not a happy string because character A at index 1 is equal to character A at index 0. So this is not a happy string. Okay, so you understood what is a happy string, and they are saying that there is a list of n size happy string. N size happy string, let's say n size happy string are these many numbers, and now we have to sort them in the increasing order lexicographically and then return the kth string. This is the problem statement. Happy string is something which is expected. Return the kth happy string of size n. So if I generate couple of happy strings from these characters of size 4, how many characters can come at this first character? A, B or C. But at second character, if I place A here, then I can only have B or C. If I place B at the first character, I can only place C or A, and so on. We have to fill all the characters in the n size string, and then this will become a happy string, and lexicographically kth string, whatever is the value, we have to return. This is the problem statement. Given is an integer n, an integer k, n is the happy string length of happy string, k is the from all the happy string lengths of size n, which is the kth lexicographically sorted happy string. This is something we should know, and in the return, what we have to return? Just whatever is the value at the kth string we have to return. If kth string is not present, then return the empty string. So this is our problem statement. I hope you understood the problem statement. First of all, let's have a look on the brute force. This is the problem statement and how you are going to approach. Brute force is something that is coming to our mind for the first time after seeing the problem statement. Problem statement is expecting that happy strings of length n we have to create, and from that kth lexicographically sorted happy string we require. So if as a part of brute force, if I generate all the happy strings, of length n, and then after that if I sort all of those generated happy string, then I can easily say what is the kth string, right? So we are breaking this problem into couple of sub-problems. First of all, generating all the happy strings of size n using characters A, B or C. no other character should be used. And then from all of these happy strings, if I sort the complete list and then return the kth string, then that would be kth lexicographically sorted string. So how do I generate all the substrings, all the strings of length n? See, let's say value of n is equal to 4. I have to generate all the happy strings of size 4, and I can only take characters A, B or C. Then at the first place I can either place A, B or C. The state will look like this after first placement. And after that, at the second position, we have two possibilities, either place B or C. If I place B here, it will look like this. At the third position, we also have two possibilities, either C or A. Now this is the state. And at the fourth position, we have two possibilities. We can't place C because C is the previous character. Either place A, B, C, A, or place A, B, C, B. These two possibilities are there. And now these two strings are of length n. So these two are my possible happy strings. These two are my happy strings. And there might be so many happy strings that we are going to capture. So from this recursion call, if I just keep on doing this, going here and then two possibilities, and then again two possibilities here, two possibilities here, two possibilities. So you can see it's sort of a binary tree. At the first position we are three possibilities, otherwise it is binary string. So at every step we are filling one character, and after filling n character, how much time we have utilized? In short, what is going to be the time complexity? Every step we have around 2 operations, so it will be around 2 raised power n. You can think in terms like this. First character we have 3 possibilities, so just only a single case. Second place we have 2 possibility, multiply all the possibilities, it will be around 2 raised power n. Let's ignore this 3 and consider it 2 as well. So we need to do the approximation. Approximately 2 raised power n possibilities are there. It means after completion of every call, we are going to have 2 raised power n happy strings. So first step is generating all the happy strings, and if we generate all the happy strings using backtracking, we will be taking a time of 2 raised power n, order of 2 raised power n. This means that 2 raised power n will be the total number of happy strings. Happy string number is 2 raised power n, and every happy string is of size n. So what is the space we are taking to generate all the happy strings? Around 2 raised power n. The same number of happy strings we are going to generate, and every string is going to be of size n, but in general the time is more proportional to 2 raised power n, so we are going to consider 2 raised power n as a space. See, so first of as far as what we have done is generating all the happy strings. So if you generate all the happy strings, you will be generating 2 raised power n happy strings in 2 raised power n time. Let's say this time is m. Okay, and how many happy strings we are having? We are having around the same number of happy strings to its power n, because when the recursion call is getting over, we'll be having one single string. So this 2 raised power n is equal to m. What I'm trying to say is that we have to sort m happy strings. To sort m happy strings, how much time do we take? M log m, right? M log m happy strings do we take, and m is equal to 2 raised power n. 2 raised power n log base to 2 raised power n, it will become equal to n into 2 raised power n. So this is the time complexity for our approach, from our brute force approach. Returning the kth string from the list is not going to take some time, and the space complexity is also in the order of 2 raised power n. So we are utilizing too much space in this approach because we are calculating all the happy strings. Let's say the value of happy string is 10 and we are creating 1000 happy strings recursively. then there is no use of generating all the happy strings after 10. So this was our brute force. We are not going to deep dive the code for this generating happy strings, because the next approach is also the same. The sorting you already know, and the returning k string from the list is like get k. Now if we try to make a bit of optimization into this, we can do something like that. Whether if we require only 10 strings, then what was the need of generating all the happy strings? So now we will come to our approach, which is optimized recursion. In this case, this is the main factor that we have to keep in mind. We have to generate strings lexicographically sorted. See, we have to generate a length and size string of using these 3 characters. If we have to use these 3 characters, and if I use these characters in this order only, so the resultant string are going to be generated in the lexicographically sorted order automatically. Why? Because first of all, I am exploring all the possibilities starting with A, then all the possibilities starting with B, all the possibilities starting with C. Definitely these will be generated first, because it's recursion. This call will get over. In the next step, we have 2 possibilities. B, if it is B, it will be AB. If it is C, it will be AC. So all the strings starting with AB will be generated first, and so on. So if you just have a look on this tree, we are automatically generating all the strings in the lexicographically sorted order. When the string will become over, let's say we make a big dry run, 1 2 3 4 4 size string we have to generate, and all the possible characters we are having is A, B and C. At the first place we have 3 possibilities, A and then B and then C. So first call will definitely be coming here. Now the possibility is this is the state, and at this moment the next character is going to be either B or C. So let's take B first, because we are taking these characters in the sorted order. Taking B first, and then when I'm coming here, I have 2 possibilities, A or C. A, B, I will be taking A again, and then one more character, and then what else? A, B, A, B. So this is the lexicographically shortest string. And what is the other possibility? A, B, A, C. This is the second string, and at this position we had 2 possibilities, either C or A. A we have already used. Now is the time for C, and this will lead to 2 possibilities, A, B, C, A. A, B, C, A, and A, B, C, B. See, if you just have a look, these strings are already generated in the lexicographically order, AB, 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 AC. So let's say this is the first string, the second string, third string, the fourth string, and when we will be covering the kth string, we can directly capture that somewhere. We are capturing that, and also we have to do something, that we are closing our recursion stack. So let's say if the value of k is equal to 4, when the recursion tree will look like this, it is coming here, here, and then going here, and then going up, and then going here, and then at this moment, and this moment, if the value of k was 4, we have found our answer, and we have to close the recursion tree. And how do we close the recursion tree? Just by handling in the recursion. Like let's say if you are making a subsequent call, do we have to close the recursion after this call? You can just pass on a parameter. If you have to close it, yeah, just close it. If solution function is true, return true. Return true means it is not moving further. It from this if condition, it is returning true, and in this way we can keep on returning. And in the terminating case, we can have a check that we can have a answer captured, because when the k will become 4, it will be capturing answer in some other string, answer string, and answer string you can initialize with empty string in the starting. right? So don't worry, like when we will be writing the code for this approach, you will get more understanding. So in this case, what we have done, we are generating k happy strings. We are not generating 2 raised power n happy strings. We are generating only k happy strings. This is clear to you that we are generating 2 raised power n happy strings. So time complexity will be in the order of 2 raised power n in the worst case. This is for the worst case. But we also need to check one thing, that every time we are concatenating these strings. So this A, B and one more character is being concatenated to this. So this string concatenation also require order of n time, because let's say when A, B, C, D, we are concatenating, let's say A again after this string. So the new string generated is A, B, C, D, A. So this operation also take order of n time. So order of n time also for this operation. So in the very worst case, it will go till n into 2 raised power n order of time. But what about the space complexity? Space complexity is we are not capturing these strings anywhere. We are concatenating a value into the string. Let's say concatenating A, B, C, D and A, and then this string is formed. Otherwise this string I'm passing it to the next function. So just to save time, we can do it in the order of n time. If we keep on clearing like whatever string we are not required. So what I'm saying is we are not using any extra space to store our generated strings. Whatever string we are maintaining, in short you can say current string that we are maintaining to capture my current string so far. Let's say current string is AB and then one more character. So this string, to store this string, we are using some space. This will be the time and space complexity for our optimized recursion approach. Now we will code this approach. Let's start writing the code for this approach. First of all, I'm going to call a solution function which will generate all the strings, and whenever it is the kth happy string, I'm going to capture that somewhere. Where I'm going to capture that? String answer. What is the default value of answer? Default value of answer is this. And I'm also moving these variables to global variables so that I don't want to pass these variables inside my solution function. To avoid clutter, I will do this. This dot n is equal to n. This dot k is equal to k. What else? We also require all the characters that we are allowed to use. Character array characters, and this characters is equal to new character array, and this character array is going to have characters in sorted order, A, then B, then C. Okay, these three characters. And in the solution function, I'm going to pass that start filling the happy string of size n starting with 0. This is the first parameter. What else? Second parameter is going to capture my string. String is blank in the starting, and in the end I must have captured the kth happy string. I can directly return my answer. This is our main function, and now I will be writing my utility helper function. For that, it's a private function which is going to take index, and apart from that a string variable that I call temp. What this should return? It should return boolean. You will understand in a while why I'm returning true. See, first of all, let's take care of the edge cases. Edge case is index is equal to n. See, index equal to n means it is a happy string, and now I need to check whether it is the kth happy string or not. For the kth happy string, it means, let's say I will keep on reducing k. If k equal to 1, it means kth happy strings, else k minus minus. It is not the kth happy string. I have to keep on checking further. It means in this case I am returning false, and in this case I am returning true. Returning true means I have found my answer. No need to check further, and the answer will be captured in this answer variable. Okay, So now my terminating case is completely working done. Yeah, I don't think something is required. And then what I have to do is I am not at nth index. I am at index 0, 1, 2, maybe some other index. So let's say if it is index 0, I have three possibilities, A, B and C. So possibilities are from this character, ch from characters. We have three possibilities, and then among these three possibilities I can pick the character only if it is not same as the previous one. Current character is ch. Where is the previous character? Previous character will be in previous variable. Okay, if previous character is not equal to current character, then take this character. And how do I get to know this previous character? This previous character will be based out. Let's say if the temporary string's length is empty, temp dot length is equal to 0. In this case, what is the previous character? Previous character is out of scope. It means we have to take all the characters. So none of the character is matching with this x, so just take it x. Otherwise, whatever is the last character, temp dot character at last index. Last index is temp dot length -1. Okay, now I have current character, previous character. If they are not same, just take this character. Taking this character means making a solution function, incrementing the index, and in the temporary variable appending the current character. And now this solution call will keep on making this solution call until we have found the answer. If it is true, just stop it. If it is false, keep on doing it. So just add one more condition for that. If this value is true, then return true. No need to do something. Otherwise, keep on exploring further. Okay, let's say I have captured my kth string, and in this case I'm returning true and then not moving further. Otherwise, if you are not able to find the answer, in the end return false. Edge case and making subsequent call. Subsequent calls are 2 in number, or approximately. First time it is 3, and all the subsequent call it is 2, and then returning false. So this is my main function. I'm calling my helper function with index and temporary strings. None of the other variables I am passing in my helper function. So I have taken those globally. Let me run over sample test cases. Nice, sample test cases are passed in the first attempt. Hopefully, I'm submitting the problem. This is submitted successfully. I hope you understood the approach. Thank you guys. Bye bye. And there might be so many methods to solve this problem, but see, recursion is the most important thing if you are preparing for tier 1 companies. So utilize these kind of problems to build your recursive thinking. Thank you guys. Bye bye.